Here we are in Unit 2, class number 10. This is the third class in combustion system components. So I want to say that you can see in the upper right-hand side of your screen that this is revised, and the reason that it has that notation is that I made a simple error when I copied the opening slide from the previous PowerPoint presentation into this one and didn't have the numbering correct. I apologize to you if you find other mistakes in any of the PowerPoint slides in these classes. One thing that you could do that would be very helpful is email the American Ceramic Society and tell them about it so I can correct these slides for any students in the future that take these courses. I do my best, but historically have been a very poor proofreader. It's because I took a speed reading course one time and I read groups of words, not individual words. And so I'm not very good at proofreading. So here we are. Let's get started. The first course in unit number 2 was the first class in unit number 2. It was about fuels combustion, combusting gaseous fuels. The second class, that's the previous class, number 11, was about burners. This class is about combustion system components. And then the next class is going to be about control of combustion systems. Now, I want to say very clearly in the beginning that I'm not trying with this class to educate you to the point that you can design combustion systems. So you need a lot of experience and perhaps some assistance from the manufacturers of the equipment here in order to do that safely. And remember that combustion systems are protected by laws and codes. And so you must meet all the requirements of the codes. That's why experts are required to assist you. But I do want you to be able to understand the functions of components in these systems. It's very important, and there's some things about the components that can protect you and prevent any accidents. Now, I mentioned something about components. In this course, I'm mentioning a lot about Hauck with the eSolutions software, Honeywell Hauck, manufacturers of combustion components. In addition, you heard me quote from the North American Combustion Handbook. So it's important for me to say that I'm not endorsing any particular product. Around the world, there are a number of manufacturers of combustion components. And so I'm only using information that I have at hand. So please seek plenty of advice from all equipment suppliers in any matter related to combustion systems. So we're going to start with gas and air system schematic diagrams, engineering diagrams. These diagrams were given to me by North American Combustion, which is now Thieves. And they were given to me for use in educational courses at the university. I'm still using the diagrams, but here for educational purposes in the American Ceramic Society's course. I caution you about using any diagrams because they may be copyright protected. So you must be sure that you're following your organization's policies with regard to copyrights. Now, you've seen the picture on the left before. It is actually the left side of the Swindell Dressler kiln in my research laboratory. It's one that they donated to the university for us to use in our research. And of course, this is a fiber line kiln. It's a shuttle kiln, so you can see the tracks where the kiln car is shuttled into and out of the kiln enclosure. When the kiln car is shuttled in with load, the door is shut and the firing process can begin. I don't believe you've seen the image on the right before. right side of the kill, and right beside it is the Harrop kill that you will see in some of the lectures, a smaller kill used for research purposes. So nevertheless, you can see some of the piping here for the Harrop kill. The whole idea behind the slide is that you can trace the line. So here's the airline. It's really easy to do on the left-hand picture. There's going up and over and distributed in a passageway channel that goes around the door of the kill. It goes down both sides. Here's the right side of the kill door. And that's the design, of course, to try to remove heat from the door seal and also recuperate some of the heat, preheat some of the air that is distributed to the burners. So you can see a burner here toward the front of the kill, one to the left and one on the upper left. So 3 burners on that side. And if you trace the air lines down here, you're going to see air going to a burner in the lower position. Here, there's one in the back that might be visible to you, and one here toward the front of the kill in the upper section. So these burners are not opposed in the top side of the kill. They're there to circulate air and increase the heat transfer in the top of the kill. You can also see the yellow painted, the color yellow painted lines where the gas is coming into the system and coming to the burners. And if you look closely, there are a number of other components that you may see along this line. I haven't shown you a close-up picture, but typically in teaching the firing course at the university, I have to take some time and show students a little bit about the combustion system components. Frankly, it's what I call the piping section of the course. Okay, and students being students don't always really appreciate this, but hopefully you're working in the real world and you can appreciate more that you need to be able to look at these components and at least understand what they are doing in firing of ceramics. So that's my goal today. I'm not trying to make you an expert. I'm only trying to make you be able to identify them. So here's a schematic of a gas flow train. Okay, so the gas coming into the kill position is here. Maybe that's the gas supply from the outside world. And we're going to have, number one, a shutoff valve. So we're going toward the burners from left to right, toward the burners. And have a shutoff valve. Well, you need to be able to shut this whole system off from time to time to service some of the other components that are here. And so number one, we go from the gas supply, whether that's primary fuel or backup fuel, we're going to have a shutoff valve right here. Now, later on, we're going to describe what kind of valve it is, typically what we call a ball valve. We'll go from that into a regulator. So the purpose of the regulator is to take the gas supply pressure and be able to reduce it to a pressure that is used in your combustion system. And what it actually is doing is functioning as a valve to let more or less gas into the system to create a constant dynamic pressure, meaning flowing pressure of gas in the piping systems that you have feeding the burners. Okay, number 3 is a low pressure gas switch. Remember that burners require a certain minimum amount of gas to stay ignited. Well, of course, that's there's a minimum in the combustibility of gas air mixtures in terms of percent gas. So we need a minimum gas pressure to keep this going. Now, that's an electrical switch, which is going to send a sensor to the next component into the combustion system. That's typically called a shutoff valve in common vernacular. It may be called a blocking valve in some of the literature by the suppliers, but you can see a handle on it. And so the handle is down right now, which in a lower position right now. It's not vertical. which means gas can flow in the system. If, for example, the low pressure gas switch senses too much low pressure, it's going to trip this valve and shut the system off as a safety precaution, so you don't have uncombusted gas possibly released somewhere in your combustion system. So when it shuts it off, the typical thing that we have in North America is that the solenoid valve will trip and the lever will go right to the vertical position, meaning it's off. Now, that's not the only condition that will trip the solenoid valve. If the electricity in the plant goes out, then we're going to shut off the valve. And we have a high pressure gas switch here as well, which is linked to that blocking valve to shut things off. So the flow is from left to right. And once everything is okay, above the minimum pressure, below the maximum pressure, then this blocking valve will allow gas to pass. Now, this particular diagram shows another blocking valve. That could be if gas is going to different kilns, or a number of kilns, or perhaps in a tunnel kiln in different burner groups. It's not always needed in a smaller kiln. You don't find it. But from there, you're going to proceed toward the burners. Now, you're going to have another blocking valve, another ball valve, shutoff valve, which allows you to operate the system but shut off a burner, an individual burner, or a burner group. Burner group is simply just a group of burners that use the same equipment from the blocking valve onward to the burner. Now, number 9 on your diagram is the air gas ratio regulator. Now, we'll talk about ratio regulators next time, but so what a ratio regulator does is it takes a pressure impulse from the air system and operates a regulator to control the amount of gas going to the right. So we're using the airflow to control the gas flow. That way we can stay on ratio or nearly on ratio in combustion, called a ratio regulator. Now, there's some other ways to control systems other than using a ratio regulator, but nevertheless, it's in the bulk of the kilns that I have ever been around. So we go from the gas supply into a shutoff valve, into a main pressure regulator, into a low pressure gas switch, a shutoff valve, blocking valve, into a high pressure gas switch. Everything's in good shape. We can take gas on toward the burners. Another blocking valve here, a ratio regulator, and that's going to be connected to the burners. Okay, well, that's pretty easy. These are diagrams from the North American Combustion Handbook. In this case, I'm just showing the air. I emphasize the air, the centrifugal blower that's supplying the air to the system. In this case, they're taking it around a stack in order to recoup some of the heat that's there. And it's coming through a system. In this particular case, there's a valve in the system right here that's controlling the airflow. Now, in this case, it's linked to the fuel flow electronically through a computer. So there's not a pressure impulse going from the air system over to the gas system. It's linked with a computer. That's another way to do this. And here's the gas supply coming in, feeding the single burner that's illustrated in the system. Of course, we also have an oil supply here, dual fuel burner, oil probably as a backup fuel coming here into a regulator, which controls the amount of oil that's flowing into the system. So we're either feeding gas or oil to the burner, and we're using air coming from the centrifugal blower, and these signals are linked together electronically with the computer. Okay, so now we're going to look at the individual components and give you some information on how to identify them, and that's mostly pictures. So here's a shutoff valve. Shutoff valve with a schematic here. In the open position, the gas can flow from left to right, for example, a high pressure side to a low pressure side, lower pressure side, and when the valve is rotated, then the gas flow is blocked. There's a hole through the center of this rotating sphere, or ball as we call it. And so when it's in one position, the gas can flow. When it's turned 90 degrees, there's no gas flow through here. The most important thing I can say to you about shutoff valves is that this valve position is going in the direction of the pipe. Okay, here's an inlet, perhaps, and an outlet, perhaps. But notice that the handle here is parallel with the direction of the pipes. That means the valve is open. Okay, if the handle is rotated 90 degrees, meaning it's opposed to the direction of the pipes, then the valve is closed. Now, this is exactly the way it is on my gas grill for making barbecue where I live. So you can take a look at the valve position and you will know whether the valve is open or closed. I'm not saying valves can't possibly leak, but just by using your eyes, you can sense whether the system is supposed to be shut off or supposed to be operational. Now, where did we go from the first shutoff valve going toward the burner? We went to a regulator. Now, a regulator has a gas impulse coming into the regulator and a gas impulse coming out of the regulator. Gas is flowing, and it has to flow through this little chamber here. And you can see the valve which will shut off if the stem comes down, and that valve's going to close and it's going to shut off the airflow. Or of course, it can partially shut off, and that's going to control the amount of gas that's coming through here. Opening upward or closing downward is going to regulate the amount of gas that's coming through here. The pressure regulator really regulates the flow, regulates the dynamic pressure through the system. And in this valve, it's relative to atmosphere. So there's a gas diaphragm in here. It's only shown in part here, but it comes all the way across, and it's going to oppose the movement of this particular spring right here, which is adjustable. And nevertheless, these adjustments are very rare in combustion equipment, in my experience anyway. So this is allowing the pressure to be regulated relative to atmospheric pressure. It's a flow relative to atmospheric pressure. Now, there's quite another type of pressure regulator. This is called a ratio regulator. Here's the gas flow. See the yellow line coming in and then going out. And we've got a diaphragm here, a stem that's poking upward with a disc on it to open by raising upward, or to close partially or wholly going downward. In this particular case, there's a diaphragm, but there is a pulse of pressure coming in from the air system. Okay, and it's the pressure that moves this diaphragm right here, up or down. Okay, so there's a pipe, a little tube coming from the air system, sensing the static pressure on the wall of the air system, the air delivery pipe. That static pressure is inserted into the ratio regulator. So you get more air, it's going to push this diagram up, and you're going to get more gas, or vice versa. Now you can see that this ratio regulator has spring in it, and it's adjustable. Now all these regulators are designed so that if the spring fails, which is rare, the valve will close. It's going to fall down. And that's just a safety feature of regulators. ratio regulator has a response, valve position versus flow. And we hope that this is a linear response, but depending on the shape of the closure in the disc in the valve, you can get different responses if you need that in your combustion system. Okay, well, that's covered ratio regulators and main pressure regulators in the system, and now you know that they are controlling dynamic pressure in a combustion system. So we'll go on with, here's the shutoff valve or reset valve. As I told you that here's the position downward. So that would instantly tell us by looking at it that it's set so that gas will flow in the system. If it goes straight up, right, then gas is not going to go in the system. I suppose that there are shutoff valves that would be different, but what I've told you is what's in my experience. These are typically solenoid valves that will work on an electrical signal. And if the low pressure gas switch or the higher pressure gas switch or the electrical impulse goes off from the electrical supply in your plant, particularly if you're concerned about the fan, combustion air fan, then that will trip. So these are rugged devices, usually without too many problems in plants. Typically, a lot of these are on top of a kiln, automobile, that is. Now, so we talked about shutoff valves. They shut the gas flow on or off. We talked about regulators, regulating dynamic pressure. As we get close to the burner, we're going to find a little valve that looks like this called the gas trim valve. It's a small unit. It's in the gas pipeline right before the burner. And there's a mechanism in here that allows you to do a fine adjustment on the gas flow. Now, as we have talked about, burners are designed to operate from low fire to high fire and modulate in between in most cases, but nevertheless, they have a very specific gas requirement. And so these little valves have a little screw mechanism. There's a cap on top, and if you pull the cap off or bend it away, you can insert a screwdriver here as you're making a gas flow measurement. I'll talk about that in a minute. Using a manometer, then you can open or shut this a little bit in order to trim the gas, to adjust the gas. So some of the North American literature calls it a V-port because of the shape of the disc that controls the flow. So there it is for you. And here they all are together. So you've seen the from gas supply, you've seen the shutoff valve, you've seen the main pressure regulator. You've gone through a low pressure switch to a blocking valve. You've seen that across here. The high pressure switch, maybe another blocking valve. That's the reason for the question mark. Over here to a shutoff valve that allows you to isolate a burner or a group of burners, if you will, into an air gas ratio regulator, if that's the way you're leaking the air to the gas, which is the usual case. And finally, we'll go into a trim valve to try to trim the gas flow. Typically, we're going to have some ways of connecting the manometer so we can adjust the gas flow, but you'll find that in the system. Okay, let's talk about combustion air components. And typically in kilns, we say centrifugal bore in order to supply large volumes of air. So you know that these blowers have inclined fan blades. They and pull or suck the air in here, propel it outward through the exit end of the blower. Typically, this is the way a hair dryer is used for personal grooming, so it's the same kind of idea. A lot of air uses the least amount of energy to propel the air. So you can see that the air enters here. In many cases, you'll find a filter there, particularly if you're making a glazed ceramic product. You want particles from within the plant to be entering the combustion system and entering the kiln. Well, how do we control that air? And for large volume use, these curtain valves are used, and you can see from this illustration that you can open them a little bit toward a lot by basis of where this control handle is positioned. Another way to do this is through a butterfly valve. The curtain valves are the ones that I'm more familiar with, but butterfly valves are out there with the amount of flow, depending on the position, the angle at which this locking section is open. Now we get into flow measurement, and so we're going to have the ability to measure the airflow and the gas flow in order to make sure that everything is proportioned correctly by our piping system and our components. The first thing to start with in flow measurement is the main gas meter. And the main gas meter is a positive displacement type of meter. A certain amount of gas flowing through the system will rotate the mechanism here as the gas flows through, and we'll get a reading. Hopefully you'll get a digital reading, and that'll be a lot easier for you to deal with. But nevertheless, that's the idea between a main gas meter, and you'll have that in residential situations as well as industrial situations. Now for flow within the pipes in the system, gas or air, we use an orifice meter. An orifice meter has an entrance in and an exit in. You measure the pressure on the entrance in and the pressure on the exit in. And these pressure impulses are hooked to a U-tube manometer, okay, that's filled with a fluid so that we can easily measure differential pressure. So the differential pressure is going to tell us how much gas or air is flowing through the system. And each one of these orifice meters has an orifice plate in it. And you choose a different size opening depending on what flow range you're interested in. And we'll be able to use published data to find the gas flow or airflow. Here's an illustration of how they work. On the high pressure side, the fluid flowing from left to right. We're going to have an orifice plate there, which is going to restrict the flow and create the pressure differential. So we have a high pressure side where the fluid is coming in, air, gas, and then we're going to have a low pressure side. So it's measuring the static pressure in the system, and the difference in the static pressure here, shown as delta PVC, is going to be linked to the amount of flow. That equation I'm going to show you in just a minute. Here's another representation. It's about the same thing. Maybe not quite as good, but it shows you the high pressure side, low pressure side, if that's what it is, with the U-tube manometer here in order to do the measurement and align with fluid flowing through it. You can calculate the flow using this Bernoulli flow equation. Very quickly, you can see that the amount of flow, Q, is proportional to the area of the orifice. Okay, so we know that, that's a given. We know the flow coefficient in our system. We're going to measure the pressure differential. So we've got the gas gravity here. So the variables are the flow and the pressure differential. So if we know the pressure differential, then we're going to know the flow. Well, the good news is you don't have to calculate this stuff. Okay, I'm going to show you how. So if you're using a manometer, the diagram on the left shows you a fluid-filled U-tube manometer, and there's no pressure differential. But the diagram on the right shows a high pressure side that's pushed the fluid down, and a low pressure side that's allowed the fluid to rise up. And if we measure the difference here, there are 4 units, or in this case, 4 inches. Now, the graduation in this scale in the United States is water column. Okay, water column. For weather measurements, atmospheric pressure, we're used to mercury pressure determination and a U-tube manometer. Mercury is a lot denser than water, and water can, because it's less dense, can show you very small changes relative to air. So 4 inches of water column, an inch of water column is equal to 0.036 pounds per square inch. It's very, very small. Well, that's the way it is with air movement. Air responds to very, very small differences in pressure. The diagram on the right shows you the high pressure side here, pushing the fluid down, in this case, blue water, and the low pressure side here. And in this case, we've got 3 inches of water column difference between the high pressure and the low pressure side. Well, for each particular orifice meter, you're going to have a graph like this that relates pressure, in this case, gas pressure on the side, gas flow, excuse me, not pressure, gas flow. And on the right side, if you're measuring airflow, it's on the right side. And the numbers on here are numbers for each orifice plate. So all you have to do is figure out which orifice plate you're using and go over to one side or the other to get the flow rate. The pressure drop is given here on the horizontal axis. So we've got the pressure drop right from the Bernoulli equation. We've got the size of the orifice meter, and we're going to have the flow rate, either right or left, depending on which fluid you're interested in. The good news is that if you're using Honeywell orifice meters, you can simply click on the eSolutions combustion utility, and that will help you not have to carry around Vulcans with you when you're doing measurements. Now, there's one other thing to say that's really interesting, and that is that you don't have to carry around U-tube manometers anymore when you're dealing with a kill. Folks make handheld digital manometers, so there's going to be an inlet port for a piece of tubing, plastic tubing, to bring a pressure signal in, and an outlet port down the low pressure side will come into another place, and it's going to show you the difference in pressure. Okay, and those are what I think most people are using today. So here's the whole system. This is from North American Combustion Handbook. That's the second combustion handbook, volume 2, page 113. And so we've got the blower supplying air over here to the burners. If you look carefully, you're going to see that it's also supplying air to the pilot lights in the system. And you know what pilot lights are. They're there to burn and make sure that the fuel stays ignited. The gas is coming in here and coming across through the type of diagram you've seen before: pressure regulators, blocking valves, low and high pressure switches, and into a ratio regulator. And they show the manometer right here after the ratio regulator. So it's not permanently installed. It's going to likely be used from time to time, but there are some ports where that contain a little valve where you can attach tubing to the upside and the downside of the device to measure the flow. So that way you can use the gas trim valve with the V-port gas trim valve in order to get the right flow into your particular burner. The same is true pretty much with the oil system. There's the oil components coming over here, dual fuel burner, if you have that available to you. Now there are a few other things that are mainly related to safety. One is flame supervision. There are two ways that it's commonly done in the United States. That's with ultraviolet radiation detectors attached to the burner, and with flame rods that go into the burner. So the UV detectors are sighting into the flame to make sure that there is visible emission of light due to combustion. The flame rods are making sure that there's temperature in the flame. And if you detect no emission of light or no temperature, then it's going to be connected to the blocking valve system to shut off the system. So it's called flame supervision. Here's a diagram from the internet, apparently from Honeywell, which shows devices being attached to burners. Here's the burner housing right here. Okay, so the fuel and air is attached to this burner housing, and flame supervision equipment is sighting into a port attached to the burner. The purpose of the Honeywell diagram is to show you correct and incorrect ways to sight into the flame to make sure that your burner is operating. I've heard people talk about these UV detectors become a maintenance item because you've got to keep that sight glass clean that's on the burner housing. I'm sure that any burner supplier can advise you on that. The other way to do it is with a flame rod, which sticks into the burner, into the combustion process, and provides a sense of whether or not we're having combustion at any time. So this is a very rugged system, and a lot of people prefer it, particularly if solid fuels are around that can cause the UV detectors to become non-functional. Same idea if you receive no signal from the flame rod, you're shut off the combustion system. And finally, we're going to talk about pilot lights. This is from obviously the North American Combustion Handbook, trying to advise you how the pilot light should be positioned with any one of these particular situations. Most of the burners today are electrically ignited, of course. So there's a spark plug kind of device in the burner. It's going to ignite the pilot light and assist with the ignition of the flame. So the pilot lights are very important for kiln safety. Okay, well, we've taken a pretty quick journey through a combustion system. My advice to you is to go out and look at a kiln and maybe talk to somebody that's knowledgeable about that particular kiln. If you're not, and trace some of the lines, the gas lines and the air lines, or the oil lines, and see if you recognize these components from the pictures that I've shown you today. Once again, I'll say that There are a lot of safety considerations, certainly design of these combustion systems. I don't suggest you do it yourself. I haven't given you enough information on combustion system design. That might be a whole course in itself, or maybe multiple courses. But nevertheless, I talked about some of the regulatory consequences of design and the fact that experience is necessary. We've talked about air components. We've talked about using our senses to know if the gas is on or off by looking at the position of valves. So these are very easy things for you to think about. You can always hear centrifugal blower for combustion air, so you know it's on. That's another way of using your senses. And you have flame supervision in order to make sure that combustion takes place. There's a lot more in safety considerations, particularly lighting a till, relighting a till, that I'll talk about later in the course. So where we're going from here is to talk in the next class about combustion control. And then we're going to go into a class on solid fuel combustion, which is important to you whether you combust solid fuels or not. So that's where we're going in the course. This lecture then is completed, and I wish you well.